Alright team, here we go. This is the last thing we're going to do in this class. Although there's lots of things you could do with differential calculus, this will be where we stop. We are going to find the volumes of objects, which, just to contrast with what we've normally done, we've been finding the areas of two-dimensional shapes. And the shapes that we're going to find the volumes of are called solids of revolution. And solids of revolution are called that not because they're going to overthrow a government, but because you create them by rotating a function, like in this case root x, around an axis. In this case, we'll do it the easy way, around the x-axis. So if I rotate it, it comes down like this and hits down here and creates a shape that looks suspiciously like ham. And you're going to laugh at me, but this is an actual, and I'll actually draw. So here's the ham bone, right? Here's some of the like fat. Here's some of the scoring for the cloves. So it's a ham. I actually did this once because I was making a ham from scratch that I got from a butcher that wasn't cured, and I wanted to use cure, and cure uses some expensive chemicals and things that you can't screw up. And so I had to figure out, well, what's the volume of water in my kettle after I put the ham in, but a ham's not a geometric shape, so it's really hard to find its volume. So I'd actually fit the side of my ham using an overhead projector and some markers and things like that to figure out like what the volume of the ham was and the volume of the brine. So this is actually useful. I used it once. That's a funny anecdote. I don't know that you'd ever be doing that, but another really great use for this technique, why you'd want to find the volume of this, again, not the area. This is a 3D shape, right? This is a ham. Is if you're going to machine something or build something and you don't want to use the material to prototype it, like you're making something out of palladium or out of a really expensive, hard to extrude plastic or something that's difficult to mill. You'd probably figure all this stuff out with a computer or by hand first before actually going about doing it. So let me tell you how we're going to do this. And we're going to take the ham analogy all the way to the bank. We're going to use calculus. And remember, the big idea of calculus is adding up infinity things that are infinity small. All right, and the word for that is infinitesimal. Okay, so that's what calculus is about. We talked about this before all the snow days and break. You're going to add up an infinity of things that are infinitely small. And how we're going to do that is we're going to put this thing on a meat slicer and cut it into a bunch of little ham slices, or discs, or, to the astute among you, cylinders. And we're going to add all of those up. Oops, you can't see that. We're going to add all of these up because they'll eventually make the whole ham. But they will only make the appropriate volume if they are infinitely thin. So of course, here comes dx, our local infinitesimal. So they're dx thin, and they're a disk in shape. And so we're going to add up a whole bunch of these volumes. So we're going to add up a whole bunch of volumes of the disks. So the volume is pi r squared times h, because a disk is just a fancy word for a cylinder. We usually say disk when it's fatter than it is tall. And then we can convert this to sort of calculus language here. The radius of each disk is given by the height from the center up to the top, which if you look here, that's what we call the y-axis, or in this case, the root x axis. So this will be root x squared. And then h, in this case, is the thickness of the ham, and that thickness is what we call dx. So we've converted all of these pieces into things that make sense in calculus. Now to add them all up, well, that is done with an integral. Remember, Sammy the Snake means integrate. So we're going to integrate pi root x squared dx. So this is a summation of a bunch of disk volumes. All right, so this is area of the face, and this is the height. Okay, and so now we need to pick how big our ham is, and let's just make it, super easy. Let's say this is 0 here. This is 0, and then this is 2. So we're gonna cut it from 0 to 2. Maybe it's 2 feet long or something like that. Big pig. So 0 to 2. So this integral right here represents the volume of this ham. So that equals v. That's kind of magical, right? I mean, we're using a two-dimensional idea with one variable to represent a three-dimensional shape. So now we just carry through the mathematics. The pi comes out. The square root of x squared is x dx. So this becomes this. You can fast forward through this if you want. This becomes pi x squared over 2 from 0 to 2. And then fundamental theorem of calculus tells us that that's going to be 2 squared over 2 minus 0 squared over 2, all times pi. So the volume in this case is, in fact, let's see, 2 squared divided by 2, those cancel, that's a 0, so the volume here is 2 pi, right? I hope so. I'm sure you'll tell me if I'm wrong. So that's fantastic. The volume of that is 2 pi, and I don't know what units we used. Maybe centimeter or feet, who knows? So cubic feet, right? So units cubed there on the end. Okay. So the general formula here is that the volume, so the disk method, right, is in fact the volume from A to B of pi, the r function squared, okay, radius function squared, times dx. So this represents the area of the circular cross-sectional face. And this guy represents the height of the rectangle, which we would call the thickness, or dx. So this is an equation of a cylinder. Okay. Fantastic. I'm going to show you one more example, and then you can go ahead and do this in the book. I think it's chapter 6.2. I don't know. Just look up disk method. You can use a table of contents. So let's do one more. We'll do some more difficult ones in class, but just to show you one more example. Well, that really marks up the page, doesn't it? One more example. Let's try one that is in pieces. So let's do one where it is a parabola and then a straight line. Okay. And we'll say this is 10. This function right here is x squared, and this right here is 4. So this is the function y equals 4. Okay, and this is the x-axis. So if we rotate that, we're going to end up with a shape that looks like this, which I don't know what that would be. Some kind of like fluted, strange trumpet bell or something like that. This is a 10, don't forget. So if we set that integral up, we're going to actually break this into 2 pieces. And we're going to do this section right here, which kind of looks like a tent. Right, if I draw it out, it looks like a trumpet bell. And then this section right here is just a straight up cylinder. So we're going to put those 2 together. And then we're going to slice them, of course. And then this one stays the same. So this is, we're putting that on the meat slicer. So add all of those up. And we do that by putting them in an integral. So the first integral is from 0 to, let's see, where would they meet? At 2? Yeah, because 2 would meet 4 here. So from 0 to 2 of x squared squared pi dx plus this one, which is going to go from 2 to 10 of the radius function 4. Notice the radius never changes. It's always 4 on this span. But over here, the radius did change. It went up to x squared. So this is 4 dx. So again, face of, pi, sorry. Face of the circle, height, face of the circle, height. And now we just push through the mathematics here. So we end up with pi times the integral from 0 to 2 of x to the 4th dx plus 16 dx from 2 to 10. And notice I pulled the pi out of both of these because they both had one, so I just pulled it out in front of both integrals. And now we'll finish the integral off here. So this becomes x to the 5 over 5 from 0 to 2 plus 16x from 2 to 10. Remember, this is x to the 0 here, so it goes up to x to the 1. This is x to the 4, it goes to x to the 5. You ought to be good at that by now. So we get pi times 2 to the 5th over 5 minus 0 to the 5th over 5 plus, this is this plus sign, plus 16 times 10 minus 16 times 2. Okay? And then we can figure that out. I don't know what 2 to the 5 is. What's that, 128 probably? Or something similar. And this one's going to be 0. Right, this one's going to be 160. This one's going to be 32. So, I don't want to screw that up for you guys. 32. Hey, who knew? So, 32 over 5 plus that times pi equals the volume. So let's just take a look at that for a second. What we've got here is this 32 over 5, which is not very big, right? That's something like, 6, 7-ish. That represents this. So, this times pi represents this trumpet bell here. And of course it's really small. It doesn't take up very much room. This 160 represents this shape if it had gone all the way back here. But it didn't because we lost it. And the 32 represents this space that we've lost. So this all kind of starts to make a little bit of sense. And then you can do the arithmetic to figure out what this is going to be, but we don't really care about the answer. So this is a good enough final answer for this video. All right, team, so try some problems from, I think, 6.2. Just look up disk method. The Khan Academy video on this is pretty confusing, but you can check it out if you'd like. There's probably other ones on YouTube. But I hope we have school tomorrow. I miss you guys a lot. We'll see you soon.